So in this example problem, we're going to solve for, we're going to determine the length and the direction of our position of the elastic rubber band that is stretched between points A and points B. All right. So to determine the length from point A to point B, we're going to use our position vector. So we can say that the position vector from point A to point B we just defined in the last lecture as being equal to the difference between the position vector of point B minus the position vector of point A. Okay, so we can first define RA and RB. So we'll say R of point A is going to be equal to X of point A. So point A is 1 meter along on the x-axis, so we'll have its x component will be 1 meter. It is along the xz plane, so the y coordinate of point A is going to be equal to 0 meters times j, and then the z component of vector of point A is going to be equal to a negative 3 meters because it goes along the negative z-axis. So we can define R of B in a similar fashion where if we look at our coordinates here, we're given that there's a 2 meter length that goes along the negative x-axis, so that would be our x value for R of B. And then the y coordinate we were given was also 2 meters along the positive y-axis, so this would be equal to positive 2 meters times the unit vector j, and then the height of point B is equal to 3 meters, so it would be equal to 3 meters k. All right, so we can define RAB from point A to point B as being equal to the difference of RB and RA. So we're going to subtract RA from RB. So if we do that, we would get minus 2 meters minus 1 meter times I plus 2 meters minus 0 meters times J plus 3 meters minus negative 3 meters times K. So if we get write all that out, we get minus 3 meters times I plus 2 meters J plus 6 meters K. Okay. So once we have our position vector RAB to determine the length from point A to point B, that's just going to be equal to the magnitude of RAB. To determine the magnitude of any vector, we can use the square root of the sum of the squares. So we're just going to square all the components together of our Cartesian vector. Alright, so if we do all that, we end up with 9 plus 9 meters squared plus 4 meters squared plus 36 meters squared, which is going to be equal to 7 meters in length. Okay, so that's our first thing that we were looking for. And then the second thing we were asked to find is the position vector from point A to point B, or its direction. So the position vector UAB is going to be equal to the vector RAB divided by its magnitude, and its magnitude is just the same thing as its length. All right. So if we just divide each of our components of RA and B by the magnitude, we'll get our unit vector. So we'll get minus 3 over 7 times I plus 2 over 7 times j plus 6 over 7 times k. All right. So just to conclude to recap what we did here, I guess the one thing I want to mention before we go too far is that once you have the unit vector, if you were asked to determine the coordinate direction angles, alpha, beta, and gamma, all you have to do is set the x components equal to cosine alpha, the y component equal to cosine beta, and the z component equal to cosine of gamma, and you can solve for the coordinate direction angles by just taking the inverse cosines. All right, so last thing here, just to recap, to determine our position vector RAB, we first had to determine the coordinates RA and RB. Then we took the difference by subtracting the endpoint of our vector minus the starting point of our vector. Once we had our position vector in terms of Cartesian coordinates, we could take the square root of the sum of the squares to calculate its overall magnitude, and then we then took that overall magnitude and divided it with each of the, or I should say, we took our position vector and we divided by that magnitude to get our unit vector. And our unit vector is defined as the direction from point A to point B.